we need to relate these angular rates with the rate of change of Euler angles. So what needs to be done is we have r dot equals s of omega r, the same as what I wrote down earlier. So s of omega is just post multiply with r transpose. Now this is going to be very specific to the choice of Euler angles. If you in this class we're using the Bryant angles, which is 1, 2, 3, r equals rx times ry rz. So this derivation will change depending on what is your choice of Euler angles. So here we use Bryant angles. 1, 2, 3. So if you have r is this, then r transpose is just that. And then when you want to, what we are trying to do here is this. In order to find the relation, we are trying to take this expression and put in the values for r, which is rx, ry, rz. So r dot, which is this term, is going to be, by chain rule, you take the derivative of each of those terms and then substitute this. So took this is the same as that, but now I substituted the values of r. Okay, so it's a kind of lengthy derivation where you need to take each of these parts 1, 2, and 3 and then go about simplifying, and it's just not worth my time here, class time, to show this. But if you want, you can see it. But what comes out of this is that after doing all the math here, what we get is that omega, which is the angular speed, which is related to r dot, is this expression phi dot I plus rx times theta dot j plus rx ry psi dot k. Okay, and then the note is here is that this is only true for 1 to 3, right? 1, 2, 3 Euler angles. This is not true for any other representation because you need to go through the whole derivation. Okay, and the derivation takes this derivation will take me like 15-20 minutes to do. Now I'll show you a shorter route to get the same formula without going through this whole exercise of writing r and expanding it out, take the derivative. There's a shorter way of doing this, and that's the way you could do it for other things too. So here is a shorter way. It's based on just figuring out this formula based on how frames rotate when you apply rx, ry, rz. So here we have a shorter derivation, and this one I'll do it because it won't take much time. Okay, so we have another method to relate omega with p dot theta dot psi dot. Okay, so what we'll do is let's just draw the frames x, y, z, and per our convention of Euler angles, we start with the rotation about the x-axis, right? Rx comes first, so we rotate about Rx. So this axis will not change, but y will shift, something like this, and the z will be something like this. So z dash y dash, and then I'll redraw x, y, z is x dash, y dash, z dash, and then this undergoes say the next rotation. Now that rotation is about the y, so y and will be the same as y prime, but double prime, right? And then this would mean that this will go here, double prime x double prime. Okay, now omega okay, is simply phi dot x plus, so phi dot, so the first rotation is about the x-axis. There's no, this is like a planar rotation. There's no problem with that, right? The second one, however, is about y. So it's about y prime. So here we need to put theta dot. Okay, so the axes have changed. And then finally, we have psi dot is about z. So this will go under rotation, which I'm not shown. Okay. So remember, I said omega is not equal to omega x I plus omega y j plus omega z k. And this is the reason, is because you don't get rotations about ijk. Ijk is in the base frame. This is like the frames keep changing, so this is not true. Anyway, so what you can do is, by using this, which I think is right, just this part has to be, I need to figure it, think about it. Omega comes out to be phi dot x plus rx y plus rx y z. So this is basically phi dot I plus rxj plus rx ry k. Sorry, I'm missing the angular rates. So this will be theta dot, which is a scalar, times y plus rx ry psi dot z. Okay, so the way to get this is you'll write I as 1, 0, 0 plus rx times, so rx, is the rotation matrix with 1, 0, and I'll not finish it, but it'll be something like that. Theta dot times j 0, 1, 0 plus rx ry psi dot 0, 0, 1. So this can be done by hand, of course, but you could also do it using the symbolic toolbox. Once you do that, you can solve for omega. It comes out. So the simplification gives you a 3x3 matrix, which looks like this. One, 0, 0, 0 cosine phi, sine phi, sine theta, minus sine phi, cosine theta, cosine phi, cosine theta, phi dot, theta dot, psi dot. Okay, so you can write this as omega equals a times, I'm going to use this notation for the rate of change of Euler. Okay, so that's the formula for angular speed, omega as a function of the Euler rates. Now, if you take the determinant of a, right, this is a, you see that the determinant is cosine of theta, which actually shows you where the problem is. So if you want to compute theta dot, or the rate of change of Euler angles as a function of omega, you'll have to invert a. But now you will have the issue that when theta is 90 degrees, the determinant of a is not defined, which means the a inverse is not defined. So a inverse is not defined when determinant of a, which is cosine of theta, is 0. In other words, theta is pi divided by 2. Okay, so remember sometime back when we were talking about Euler angles and singularities, we talked about theta equals pi divided by 2 being a singularity of Euler angles. it manifests here too. You cannot find the Euler angles, the rate of change of Euler angles, when the second rotation is 90 degrees. So that's the singularity. Or the gimbal lock. Yeah, this is the expression, and then it's still useful sometimes, but there is an issue with this notation. Now you could also do another. So this is the angular velocity in the world frame. Okay, and there's another way you can express this, that is angular velocity in the body frame. So when something is rotating, you want to describe how it moves with a frame which is fixed to the earth, that is this angular speed omega. But you could also describe its movement of this body in its own frame, okay, in the frame which is attached to the body and moving with it. So that derivation also comes from a similar one, but I will just give you the answer, but I won't attempt to do it. What you need to do to get this derivation is, so this is the second rotation, Ry. This undergoes another rotation, right? So x double prime, y double prime, c double prime, and then this one will go under. The third rotation is about the z-axis. The triple prime, y triple prime, and then this is unaffected. So what you can do is you can write the angular velocity in the body frame in a very similar way as the one I wrote earlier. If the body frame is the third frame, so psi dot z triple plus theta dot so again, you circle back from the last one to the first one. You can show that this comes out to be psi dot theta dot RZ transpose triple prime plus phi dot RZ transpose RY transpose X triple. The way you'll do this is you'll write this as psi dot 001 plus theta dot. You'll take RZ, take its transpose, and then multiply it with 010 plus phi dot. The same thing here, 100. So this is something which you could do by hand or by SimPy. Okay, so don't go by my notes. I might have made a mistake in writing things down. Your best bet is to use this code because this one actually does all this for you. Define the rotation matrix Rx, Ry, Rz, angular velocity in world frame. So this is the first expression I wrote down. Okay, then we have this RWE is basically A, and then this is angular velocity in the body frame. Okay, and this code will actually print it for you. Okay. This is a better way to print this out. I think it's called sy dot pprint. I forget. Yeah, so if you use this sy dot pprint, it writes it in a better way. So you might want to do that for everything. Okay, so you can then copy this. So don't go by my answers. There's a homework. Your homework, you have to use these expressions. So don't use my expressions because I might have made a mistake.